Bismillah ar-Rahman ar-Rahim. All right, dear students, Assalamu alaikum and welcome. Uh, in today's session, we are going to discuss problem number 5.10 of your textbook, and the problem statement says a large brass washer has a 2 centimeter inside diameter, a 5 centimeter outside diameter, and is 0.5 centimeters thick. Its conductivity is 1.5 exponent 7 Siemens per meter. The washer is cut in half along a diameter, and a voltage is applied between the two rectangular faces of one part. Alright, the resultant electric field in the interior of the half washer is also given to us, 0.5 upon rho a 5 volts per meter in cylindrical coordinates. Alright, and it says that where the z axis is the axis of the washer. Washer is a simple mechanical device, we all know. It's nothing but a disc which has got a circular disc which has got a circular hole in it. All right, so it says that the diameter from the one end to the other end is the outer diameter is actually 5 centimeters, so the radius is 2.5 centimeters, and the diameter of the inner circle is given to be 2 centimeters, so definitely the radius would be 1 centimeter. And it says that the washer is not a full washer, rather it is truncated, all right, about some some diameter. So let's say this is x-axis. I think I should draw it from here. Better draw it from this side. This is one axis, and the axis of this washer itself is given to us to be z-axis. So this is nothing but a cylinder. This is z-axis. All right, I should remove these lines. So this was our original washer. We are just trying to establish coordinate axis around it. So let's take this axis to be x-axis. So definitely z-axis is somewhere along this side, all right? So z-axis x-axis will be along this line. So we have to cut it through, right? This is not the complete washer. If you cut this washer along this diagonal y-axis, so definitely things will be different. We have to assume we have to take half of this washer, not the complete washer. All right, so definitely there is some height to this washer, and this is the z-axis, and definitely if you cut it through some diagonal, you're going to get this whole washer somewhat like this. Okay, so this is our z-axis, and let's take x-axis. Let's take the y-axis along this line. This is y-axis. Okay, and z-axis actually should start from this line, because, or this point I should say. Why? Because this washer has been now cut in two halves. So this is the washer. Okay, so it will if you go down, right, this is the origin, this is the y-axis, and this is x-axis. So this is somewhat the true diagram which you should consider. X-axis, y-axis, z-axis is going like this. Okay. So this is x prime. Okay. So now much better. Okay. So what if we just change the naming of the axis a little bit? If I take this axis to be x and this axis to be y, then I think it's the same thing. It's not a big deal for us. All right. So this is brass washer whose conductivity is given to us, whose height, thickness is also given to us, and that is h, which is 0.5 centimeters. Okay. All right. So we are asked. This is the situation, and it has been mentioned in your in the problem statement that from one end, perhaps this rectangular end. Now there are only two rectangular ends, this one and this one, the two shaded one. Okay, so perhaps from this rectangular end, at this rectangular end, some potential has been applied. All right, and field has been established. So field, common sense also tells us that if we apply a potential at this plane, this rectangular plane, potential will be along, the flux lines will be along the brass, because brass offers permittivity much higher as compared to space. So the most of the flux will try to converge and stay within this brass. So the field will be starting from there, will be starting from this point, and will be traveling along the washer and terminating in this fashion. So this is electric field intensity, which has got only phi component associated with it, and it is only the function of rho, meaning as you go farther in the direction of rho, as you go farther with respect to z-axis, the magnitude will decrease, otherwise the direction would be the same. So in part A, we are asked to find the potential difference between these two faces, rectangular faces. Let's call that V0. We know this well-known formula. E is known to us, and if we are now, if we want to use this formula, E is given to us. dl in cylindrical coordinate system is nothing but d rho a rho plus rho d phi a phi plus dz az. Okay, so now remember that if you would see this situation from the top like this, let's say this is y-axis, this is x-axis, you're watching this situation from the top, so washer will be like this. But since we are considering from plus x-axis to minus x-axis, somewhat truncated washer, so we should remove these curves from here. Okay, so this is actually the washer which we should consider, which we would see if we watch this situation from the top. Z-axis is definitely coming out of the board, so electric field is like this, Z-axis coming out of the board, so electric field definitely has got only phi component to it. Okay, anyway, so now if you want to find potential difference, obviously will have to consider DL, but as soon as we'll take the dot product, since DL has got only 5 component, these 2 components would reduce to 0 because we are taking dot product. So only E written here, and for DL only this middle term, that is rho d phi, would remain. Okay, now from this, at this point the value of phi is 0, at this point the value of phi is pi. So from pi to 0, if I take a positive jet charge and move along this line, so I'll have to move from this point to this point in order to gain energy to the system. So that's the reason why we take this point as the initial point and this point as the final point. So pi to 0. Take the dot product, take the constants out, do the necessary cancellations, and we'll get the answer to be 0.5 pi volts. In part B, we are asked to find that if this field is established within the washer, what would be the total current flowing through this truncated washer. For that current, we must have to find current density, which is J. Only then we will be able to find current through this expression. Since E has been given to us already, so J is equals to sigma times E. Just replace the values, you will get J, which is 7.5 million upon rho A phi amperes per meter square. Do the maths again. All right, so this time we are finding the current in this direction. All right, so the current in this direction means that the problem statement asks us to find in part B what total current is flowing through this washer. So definitely this rectangular surface, we can take that rectangular surface as ds for this integral, because this ds is perpendicular to current density, and if you take ds, if we'll take this rectangular surface to be ds, only then we'll be able to find the maximum current which is flowing through this washer, because this rectangular surface is the only surface which is perpendicular to current density, because this rectangular surface is at phi is equals to 0, and current density is in the direction of electric field, and electric field is in the direction of phi equals to is in the direction which is perpendicular to phi equals to 0 or phi equals to constant plane. So if we take ds, which is perpendicular to j, or the direction of j is parallel to j, in that case we will get the maximum current which is being asked in part B. So for this rectangular patch over which phi is constant, we know the formula is d rho, यहाँ से लेके यहाँ तक का फासला, and height which is dz, and since we are dealing with a plane which is on radial plane, a phi. All right, replace these values here, take the dot product, take the constants out, you will get this expression, integrate, solve, you will get this current 3.4 exponent 4. A very huge current is, by the way, passing through that conductor, because that conductor is offering a very good conductivity. So a little bit of field will definitely excite a lot of electrons or charges to move from one side to another side. So that's why the current is quite huge. In part C, we are asked to find the resistance of this brass truncated washer between these two faces. It means that if we take a voltmeter and connect a red terminal, the red terminal here and the black terminal here, and set the voltmeter to find the resistance, we'll get the resistance which will be 4.6 micro ohms. Why? We know the potential difference between the two phases. We know the current which is flowing through the two phases, between the two phases. So just take the ratio to get to get 46 microohms the resistance which is required. So this is how you'll solve 5.10.